How much did we do together? Did we just do the first one? Okay. Oh, and then we picked the boxes. There was an error in my last video. You can't change the boxes in any of these cases. Um, yeah, because you can change them, but you have to change the dollar values on the tickets. So anyway, don't do anything fancy with box changing in these cases because we're calculating sums, which creates problems. So I know, I let you down. All right, suppose you plan on rolling a 6-sided dice 144 times and you win $1 every time you roll a 3 or a 5 and you win nothing on all other rolls. So in the box, I'm going to have 2 copies of 1 and 4 copies of 0. Now we can't change the numbers in the box because then we end up dividing by something different and anyway, just don't do it. Um, it messes things up a little bit on some of them. All right, what is the sum of the box? So the sum of the box is 2. The average of the box is going to be 2 divided by 6, which is 1/3. And the SD of the box is going to be the big number, which is 1, minus the small number, which is 0, times the square root of the fractions, which is 2/6 and 4/6. Everybody understand that? Why am I allowed to use the SD shortcut? There are only 2 numbers in the box. There are ones and there are zeros. Now there are multiple copies of those, which is fine, but if you have 3 different numbers, the SD shortcut doesn't work, and you have to actually plug the numbers into your calculator. What is the expected earning after 144 rolls? So we're going to take the average of the box and times that by 144, and you get 48. So the expected value is 48, and then we need the SE. The SE is going to be the SD of the box, which is the square root of 1/3 times 2/3. So that is 0.47. Now we need to multiply that by the square root of 144, so we times that by 12, and the SE is plus or minus 5.65. Everybody good with that? All right. If many people roll a dice 144 times, what percentage would we expect to earn between 40 and 56? So, draw my normal curve with the average at 48. And then I want to know between 40, which is minus 8, and 56, which is plus 8. That's nice because I can use the table. So I take 8 and I divide it by the SE, and I get 1.414. So that is my z-score. I look up 1.414 in the table and I get 0.3 or 0.84. So the answer is 84%. Okay. More than 38. So 38 is over here, and I want to shade to the right. That is a score of -10. Divide that by 5.65. And I get a z-score of -1.77. So clear out my equation, and I need to do zoom recall, and then shade norm. And I want to go from -1.77 to 5. And I get a value of 96%. Okay, and then the last one, less than 44. So that would be here and to the left. That is a score of -4. So -4 divided by 5.65 is -7.7. So clear out the draws and then do a new shade norm. And we'll go from -infinity to -0.7. And I get an area of 24%. Okay. Now I want to simulate. Hi guys. Glad I could be of service. Most useful thing I've done all day. Now we want to simulate a whole bunch of copies of playing this game 144 times. Now, if you were actually rolling the dice, you might be able to get one, maybe two versions of 144 in this class, but you'd go nuts, right? It wouldn't be any fun. And we could simulate individual copies of 144 if we had some way to pick from this box. But our calculators will only let us generate random integers that are between a certain value and another value. So if we wanted to pick numbers between 7 and 12, we could do that. But the calculator doesn't have any way of building a 110000 box. And the reason it doesn't is because why do that when we can simulate entire sets? So I know that my expected value is 48 and my SE is 5.65. So I am just going to play that game and get rid of the box entirely. If I know what the expected value is and I know what the distribution is because of the SE, then I will just simulate 48 and 5.65. And the way we do that is go into math and over to probability, and then we do the random normal curve generator, and we plug in our average, but in this case it's the expected value of 48, comma, we plug in the SE, which is 5.65, and then we tell it how many times we want to play this game. So I want to play this game, according to the worksheet, 40 times. And I want to store that in L1. So I push store, and then second number 1 is L1, so second 1, and then I hit enter, and I get a whole bunch of games of 144 rolls. So if I go into stat, I can look at these. Now, this is a little bit of a lie. How come this isn't totally accurate? There are decimals, and my box doesn't have any decimals. Well, all you have to do is round it to the nearest one, round it down, round it up, or just pretend that it's okay. That's what I would do. If we did enough simulations, the decimals aren't going to matter. Okay, so I'm pretty much not going to worry about it. And the easiest way to count these is to sort. So I'm going to go back into stat and go down to sort A, which is ascending. And I want to sort A, L1, and then that is going to put them all in a nice order so that I can count. So 96% of them should have been more than 38. So let's count the ones that are below 38. Oh, they're 0. So for this, I got 0%. Is that too far off? No, I'm pretty close. That's 4% off. Okay. So 84% should be between 40 and 56. I'm going to count how many are outside that range. So I don't have any on that end. And then if I go to the other side, I have one that's bigger than 56. So it turned out that 39 of my 40 calculations were inside that window. So 39 divided by 40, and I ended up with 97%. That's quite a bit off, right? But I only played the game 40 times. So when I teach you how to determine if that's okay, we probably would be all right. Maybe not. This might be one of those exceptional cases. Okay, then you do the same thing for less than 44. Actually, let's calculate that. It won't be too hard. So less than 44. I have 1, 2, 3, 4, 5, 6, 7. So 7 out of 40 gives me 17%, and I expected 24%. That's pretty close. Okay, and again, the more times we play, the more our observed percentages should mirror our expected percentages. And 40 really isn't very many. Right? We would want to do more than that if we could. How many do we want? The answer is lots. 500, 1,000, 2,000. Just depends on what you're doing and how accurate you want to be. Okay, next page. So does everybody understand the difference between the 144 and the 40? So in the game we just did, what does 144 represent? How many rolls every person is going to do? Okay. What does the 40 that we plugged into the calculator represent? That's how many people played the game. So what I have just done is pretended that 40 people rolled the dice 144 times. But I didn't plug 144 into the calculator. I used the 144 to create this list here. So the nice thing is the box, the number of rolls are all built inside those numbers. These numbers represent what happens when a person rolls a dice and counts 2s and 3s 144 times, which is pretty cool. That these numbers contain all this information we calculated, all of that is hidden inside there. And if I roll more times, those numbers are going to change, but they will still represent the same situation with a particular number of rolls. Okay? And it all goes back to chapter 5. Right? If you understand chapter 5, you should do just fine. Okay, next box. Suppose you plan to roll a 10-sided dice 500 times and you win $1 every time you roll a 4 or below. So in my box, there are 10 tickets. What are on the tickets? 4 copies of 1 and 6 copies of -1. Do you want to play this game? No, you don't want to, because the sum of the box is -2, and the average of the box is -2 divided by 10, which is -0.2. What does that mean? What does -0.2, or 20 cents, is how much you're expected to lose every time you play. So we are going to play 500 times. So my expected value is 0.2 times 5, or sorry, 500. 0.2 times 500. I am expected to lose $100 if I play 500 times. Now, some people asked me, does this value have to be negative or positive? And the answer is, it doesn't matter. You can either look at it in how much you lose, or you could look at it as the casino, how much they win. And our answers are our answers are in percentages. So if you want to do them all positive or all negative, it's not going to matter, because when you do shade norm in the end, you're going to get the same percentages as long as you do everything correctly. So it doesn't matter how you set them up. as long as you recognize that positive 100 represents a win for the casino, a negative 100 represents a loss for you. And outside of that, it doesn't matter what you do. Okay. The SD of the box is going to be 1 plus 1 times the square root of 4/10 times 6/10. So 2 square root of 4/10 times 6/10 gives me 0.98. Why is that so close to 1? No. What the SD of the box tells me how far, on average, how far are the numbers in the box from the average. Why is it really close to 1? Because every number is about 1 away from the average. And in the book, if you have a 1, -1 box and the numbers of each ticket are about the same, the book just calls it 1. But I'm going to leave it as 0.98. I need to find my SE. So I'm going to take that and multiply it by the square root of 500. And I get my SE is plus or minus 21.9. So, I want to build a normal curve. My EV is 100, or negative 100. And I want to know between negative 120 and negative 80. And you could build this with positive numbers, and the 80 and the 120 would just switch, but the percentages are going to be the same. That's a score of plus 20. So 20 divided by my SE is 0.91. And since it's plus 20 and minus 20, I can use the table. And 0.91 would be about 62.5. So I get 62.5%. Okay, for the next one, come out ahead. What are the chances of coming out ahead? What does that mean? You win money, so I'm going to go from 0 to the right. It's not looking very good for me, right? So that is a score of plus 100. So 100 divided by my SE of 21.9. I get a z-score of equals 0.456. Or sorry, 4.56. Should I shade norm? No. Why not? How much area is to the right of 4.56? None. Did anybody actually do it? Did you get 0 or did it? Okay. So I'm going to plug it in just to show you, because anything beyond 5, the calculator can't tell a difference. So just for fun, I'm going to plug it in and show you what the chance of that happening is. And in the meantime, I kind of need to change my window so you can see it. I'll go all the way out to 6. All right, so I want to shade from 4.56 to 5. Well, let's just say 6. So on my graph, 1, 2, 3, 4.5. So everything from here over. And it says 2.56 e to the negative 6, which is 0.0000256. We can turn that into a percentage by moving this 2 decimal places. So that's the percent chance of winning. 0. So should we run out and play this game 500 times? No. Bad idea. You're going to lose money. Lose more than $15. So that would be right here, an over. That is a score of 80. Oh, wrong. Sorry, I'm looking at the wrong paper. Lose more than 40. I was looking at the next problem. Thanks. All right, so 40 and to the left. That's a score of plus 60. So I take 60 and divide it by my 21.9. And I get a z-score of 2.73. I'll go back in and fix my window. So we will shade norm from negative infinity to 2.7. Which is pretty much everything, 99.6%. So you are almost guaranteed to lose more than $40 if you play. And then to simulate 60 sets, you're going to do rand norm of 100, or negative 100, comma, 21.9, comma 60, and then make sure that you store that in your L1 and then sort your L1 and you can count up and see what your percentages are. Was anybody way off when they did that? No? Pretty good? A random number generator is decent even though it's not really a random number generator. Okay, next one. In roulette, a 3-number bet pays 11 to 1 and you are betting $1 on a 3-number combination 225 times. So anytime you build a roulette wheel, you have to have 38 tickets in the box. So what are those tickets? We have 3 copies of 11. So let's say you bet on the numbers 1, 2, 3. If you get a 1 or a 2 or a 3, you get your dollar back, which we just pretend never happened because it makes the box easier. And then the casino pays you $11. So basically, they stack 11 tokens on top of your 1 token, and then you just take it all. Okay? And if you lose, they take your token. And there are 35 ways to lose your dollar. Now, we've done roulette over and over and over, and we always get the sum of the box is -2, and the average of the box is -0.0526. Okay? But the SD of the box changes depending on which bet you make. Now, there is a 5-number bet in roulette that has a different odds, but that doesn't even exist at a lot of places. So this is going to be 11 plus 1 times the square root of 3 over 38 times 35 over 38. What's that? It's 11 minus -1. Yeah, it's always big minus small. So the SD will be 12 times the square root of 3 over 38 times 35 over 38, which is 3.23. Okay, now we're going to play this game 225 times. So to find the SE, or sorry, the EV, the expected value, I need to do 5 cents, 5.26 cents times 225. So negative 0.0526 times 225. If you play this game 225 times, you're expected to lose $11.83. And the SE is going to be 3.23 times the square root of 225, which is 15. So 3.23 times 15. And I get plus or minus $48.45. What do you think about this? Are your chances of winning good? Better than you thought they'd be, right? Is there a reasonable chance that you're going to win? It's not terrible. right? Are in that one SE window, +1 and -1, did anybody win in that group? Yeah, the SE is bigger than the EV, so it turns out that you can win. But the problem is you have an equal chance of losing a lot. So if we wanted to figure out to lose between 10 and 20, so this is not going to be something we can use the table for. So my expected value is -11.83. I want to know my chance of losing between 20 and 10. And that's not symmetric, so we can't use the table. So that's a score of plus 1.83. So I take 1.83 and I divide it by 48.45. And that gives me a positive z-score of 0.038. And then 20 minus 11.83. Divide that by 48.45. And I get a negative z-score of 0.168. So it turns out this is really narrow. It's going to be this area right here. All right, so shade norm from negative 0.688 to 0.038, and this is going to be like 8% or 10%. I don't know. It's not going to be very much. Oh, it's bigger than I thought. 26.9. Is that what you guys got? Did I plug it in right? Oh, was it 0.168? Oh, you're right. Okay, let's do that again. Negative 0.168. That surprised me. It was bigger than I expected. There we go. 8%. 8.2. All right, what's the chance that you're going to lose money? So we want to go over here to 0, which is a value of 11.83. So clear out my draws. And I'm going to do 11.83 divided by 48.45, which gives me a z-score of 0.24. So I will shade norm from negative infinity to 0.4. Was that right? 0.4? 0.24. I did it again. 24. And it turns out you have a 59% chance of losing, which is probably a lot lower than you would expect. Okay? But the bad news is the chance of landing right here is the same as landing right here. So it's true, you might come out ahead, and lots of people will. In fact, 40% of them will. But on the other side, those people will lose a lot of money. So in either case, it's just not a good idea. And then you could also do lose more than 15. I'll let you guys figure that out. All right, the last one. In roulette, a single number bet pays out 35 to 1. You plan on betting $15 on the number 7 1,000 times. So we have to have 38 tickets in the box. Only one of them is a winner. And what is on that one ticket? Well, imagine you put $15 on the number 7. When you win, they are going to stack money on top of that that's equal to 35 times what you bet. So they'll put 35 $15 bills on top of yours, or tokens. So 15 times 35 is 525. Boy, that's good news if you win. But what else is in the box? 37 copies of -15, which we don't like. So when I add all that up, so if I add 525 plus 37 times -15, I end up with an error because I didn't type it in right. Oh, I put -15. So I get the sum of the box equals -30. Could you have told me that without drawing the box? Let's think about it for a second. Why does that number make a lot of sense to us in roulette? What is the sum, the normal sum of a roulette box if we bet $1? -2. So this one is -2 times 15. So all we've done is swapped out our $1 bet with a $15 bet, which makes the average of the box 15 times larger than it would have been normally. Okay? So if I take that -30 and I divide it among 38 tickets, I get the average of the box is -0.789. How would I have figured that out without the box? It's probably going to be equal to my old average, which used to be 5.26 cents times 15. So 0.0526 times 15, what do you know? 79 cents. Okay. The SD of the box, am I allowed to do the SD of the box? Yes. Or am I allowed to do the shortcut? Yeah, of course you're allowed to calculate the SD. I can use the shortcut because there are two types of tickets in the box. There's a 525 and there are -15s. So I do 525 minus negative, which is plus 15, times the square root of 1/38 times 37/38. So 525 plus 15 times the square root of 1/38 times 37/38, and I get 86.4. Okay. My expected value in 1,000 draws is going to be -$789. Right? Just times the what's it called? Average. Times the average of the box by 1,000. Now my SE is going to be plus or minus my SD right here times the square root of 1,000. Which is 2,733. Is there a decent chance that you're going to win some money if you play this 1,000 times? Yeah? Yeah, 789 is well within the SE range. But again, the problem is you might also lose a whole bunch. Okay, you're expected 1 out of 37 plays. So 1,000 times 37. Oh, geez, that's not what I wanted to do. 1,000 times 1 over 37. So you're expected to win about 27 times. But you might win 30 times. So if I won 30 times, 30 times 525 minus, so if I won 30 times, I would lose 970 times 15. So if you won 30 times instead of 27 times, you'd make $1,200. Sounds like a great plan, right? Unless you're unlucky. So instead of winning an extra 3 times, what if you lose an extra 3 times? So that would be 24. 24 times 525 minus 976 times 15. So if you're unlucky and you actually lose more often than you're expecting to, then you lose $2,000. So still not worth it. There is a chance that you could win a lot of money, but not really. Now, here's a question. What if I changed the box to betting on red? Would this number change? No. Because if I bet on red, this is exactly the same for any bet on roulette. So that would not change. If I bet on red, would this change? Yes, because that number is based on the SD, which is based on the values of the ticket, or the percentage of the tickets in the box. Okay, now this is a pretty advanced question, but if I bet on red, this number does not change. This number will change. Is it going to go up or is it going to go down? Down. Why? Will betting on red even out sooner or later than betting on a single number? Sooner. So if it evens out sooner, that means that the SD is going to be smaller, which means that the SE is going to be smaller. So if you're going to play roulette a lot of times, do you prefer to bet on red or do you prefer to bet on a single number? Depends on what you want, right? Do you want a chance of winning a lot of money and a chance of losing a lot of money? Or do you want to be guaranteed to lose a lot of money? Do you see what I'm saying? Betting on red 1,000 times, you're guaranteed to lose money because your SE will be really small. So here are the two graphs. Both of them will have negative 789 right here. Okay? But if we bet on red, then my SD is going to be pretty small. I don't know what it's going to be. Well, maybe I should figure it out. 540. 540 times the square root of, that would be 18 and 20. 18 38 times 20 38. And then we times that by the square root of 1,000. Hold on, I messed something up. 15. What did I mess up? Anyway, didn't work. I'm getting way off topic. All right. Oh, that's good. You guys can do the last bit, right? No? Do you want me to do one? Okay, so between 750 and 850, and my SE is huge. So it turns out that's super thin. Did you get practically zero? 1%? Yeah. That maybe I'll change those for future. What's your chance of winning money? This will be, we can actually do that. That's a value of plus 789. So 789 divided by 2733. And we get a z-score of 0.28. So if I shade norm from 0.28 to 5, what does that give me? Like 25%? What'd you get, Dex? 38%? Okay. And then the last one, lose more than 200. That's going to practically be the opposite of 38%. Did you get 62? 60? 58? 58? Okay. All right. We're done.